Hi everyone. So you all heard about impressive deep learning models, but this whole thing may sound really complex and really hard to understand. However, all these 100 billion parameters state-of-the-art models that you hear about are actually under the hood implemented as a small set of generally easy to understand abstractions, so-called operations, and basically a couple of algorithms that know how to propagate information through these operations back and forth. By following along this video, you will deeply understand how a deep neural network library is implemented under the hood. And that's because we will build a minimalistic version of such library ourselves, absolutely from scratch. So we will not rely on any abstractions that somebody else implemented for us. Rather, we will start from empty files and build all the abstractions ourselves. We will write the code together with you, very gradually, step by step. And it's also not one of these videos where you don't get to see anything but code. And instead, I try to provide a visual understanding first and foremost. Also, when we are going to implement some abstraction, something in the code, I'll try to make sure to lead up to that point with some examples and some prior knowledge. What we're going to build by the end of this series is not merely a specific neural network architecture, but rather a toolbox which allows you to implement almost any neural network architecture that you care about. And because you follow along, you will have actually implemented this toolbox yourself absolutely from scratch. What you see on your screen is the result of the first few videos in this series. By the end of the first couple of videos, we will have implemented a set of a dozen operators and their backward passes, the autogenerated engine, multidimensional tensors, the tensor abstraction itself, and a graph visualizer. Don't worry, this was just an extremely high-level overview. We will go over each of them in much more details. I'm just deliberately staying at a very high level for now. Finally, before we begin, let me just say a couple of words about myself. I work as a machine learning engineer at an MIT-based startup, and I've been in the field of deep learning for more than 5 years. I published or contributed to a few publications, few research papers in the field of deep learning. As the series progresses, I plan to add more and more features to our library. For example, we might start by adding even more of these operators as to expand the range of neural network models that we are able to implement and train within our library. And then gradually, we will start shifting towards implementing some of the latest and greatest architectures that you probably heard of, such as diffusion models, the transformers, and many others. Additionally, we will add support for more core features, such as support for strides, maybe sparse tensors, fancy views and indexing into our tensors, and so on. Right? The list goes on and on. We will also consider adding a Python interface for our library, because most of the people, they use a Python language so that they're able to interact with our efficient implementation of the library which is in C through Python. Right? So this will be an interface that many more people that can relate and program in, so that we might want to consider this in the future. And other features, of course. A disclaimer before we begin. Don't expect whatever we're going to build in the end to be on par or exceed any of the well-known deep learning libraries on any metric, because the purpose of this video is purely educational. So we'll focus on learning what are the components of such libraries are and how do they interact with each other. But we'll focus on building smallest, simplest version possible. Okay, let's start coding, right? Well, this video is also an intro to deep learning, as I mentioned, so we're going to need to cover some basics here. Now, keep in mind, whatever we're going to learn here will generalize to any optimization, any real-world problem that you can care about. But for the sake of a concrete example, imagine that the task that we want to perform is image classification. So, given an input image, we want to create an algorithm that will take in this image as an input. Image can contain some objects, right? Let's say our image has a cat, and let's say there's some other objects as well, a tree, something like this. And the output of our algorithm should be a class label for one or more objects that are contained in that image. So given that problem definition, what should we write in this function? And this problem here is really unlike any other problem that you worked on in computer science. Typically in CS, we are able to express our algorithms as a very well-defined, well-behaved things. So typically, let's say we have a problem of a tree traversal, right? So we just defined a tree, and we know that each node, let's say, has a left and right child. So when we are at a node, it's trivial for us, right, to know how to traverse the tree, right? We're just repeatedly doing this thing. We can go to the right tree, to the right parent, we can go back, we can go to the left parent, etc. Right? Another problem that you can be familiar with is sorting a list. So let's say we have some numbers here, and we organize typically in CS things in such a way that it's trivial for us to go from one element to another, right? So we define our data structures in a way that it's really convenient for us to traverse them or do whatever operations that we might care about, right? But note about this thing on the left that we talked about. These two kind of sets of problems seem fundamentally different, right? So specifically, natural images that we care about on the left example are very different from these well-behaved structures on the right. And natural images don't have a well-defined structure to them, right? Apart from the fact that image itself consists, basically, is a grid of values, you can't expect more structure to images than what we just described, right? Any combination of pixels can result in some object that your algorithm needs to deal with. Well, let's say we are very determined and try to ignore these problems that I just outlined. So let's say we still decided to pursue and implement some algorithm to classify images. One way how we might try to tackle this problem is by basically encoding our human knowledge and intuition in the algorithm. So specifically, when I look at this image, it makes sense to me that some of the features of each object are salient and important for detecting that class of objects specifically, right? And these features are different from features of other objects, right? So these are the ones that differentiate objects of each class from others. Specifically, for that image, right, we might think that cats typically have two eyes and a mouth somewhere below the eyes. So we might actually try to create some bank of filters. For example, let's say one filter will specialize in identifying some circular objects in the image, and this would correspond to a cat's eye. Well, at least in my image. And we have another predefined filter that we as humans hard-coded into our algorithm that will activate whenever a cat's mouth is detected, or some approximation to the mouth, right? Well, then we can define an algorithm that will basically take our filters and will just slide through the image like this. And whenever our filter overlaps with underlying pixels of the same shape as the filter will activate. So this will signal to our algorithm that this particular feature is detected in the image. And we'll do the same for this filter. We're going to take that and do the same. We're going to slide it through the image. And now, whenever our smile filter comes across cat's mouth, it'll going to activate as well. And in general, we can have an arbitrary number of predefined filters. Now, you can see that this is probably not enough, right? Because maybe there are some other circular objects in the real world that aren't cats, right? So specifically, my human intuition additionally tells me that, well, generally cats have their eyes and mouth, in some kind of specified relationship with each other, right? So specifically, typically I don't see cats like this. Cats who have their eyes right here and the mouth maybe like this. You can see that this is typically, not a valid cat, right? At least I didn't see one. So you can see that this roughly corresponds to encoding even more human knowledge into our algorithm, right? So specifically, we will need to implement some logic to basically say, okay, not only we need to extract these features from the image, not only we're going to need to encode these filters, but also we will need some additional logic on top to basically, specialize or handle the relationship between these salient features that our algorithm detected. Now, you can see that this gets out of hand very quickly. Specifically, let's say that now we want to tackle a different problem. Let's say we want to detect cars now, or trees, right, for that matter. Now, whatever logic that we hard-coded right here is basically irrelevant anymore, right? So we just wasted kind of our human efforts specializing for a particular object, but then, in the real world, we can have thousands and thousands of other objects. So what are we going to do? Let me give you a second reason why that algorithm is not really good. And this is just empirical reason. So in reality, we know people try this approach. It just doesn't work nearly as good as other possible approaches that we're going to discuss next. So essentially, it's a very cumbersome approach in practice. It requires a lot of hard-coded knowledge. It requires a lot of human wasted hours of writing this logic. And additionally, it just doesn't work good, right? It just works really badly. So there's no really good reason why we want to go this route. If not for this approach, how else can we solve this problem? Well, we want to use an optimization-based approach. In other words, we want to create a model which is able to learn from the data and basically slightly adjust its parameters in order to predict the correct class better and better. By repeatedly applying this approach, our algorithm will so-called learn how to correctly classify images in this case, and in general, it will learn to perform almost any task that we're going to throw at it. Then it will be able to perform that task correctly as well. And so the rest of this video is exactly about that. We're going to go step by step. I will explain all the mental models leading up to actually us implementing a simple neural network, which will be able to tune its parameters in order to correctly predict the actual label. To explain the learned approaches better and to have an easier time developing our intuitions about these approaches, we're going to want to simplify a problem for a moment. So suppose that instead of classifying objects in images, we have a different task. Our task is to predict a y coordinate from an x coordinate. So suppose there is some x coordinate that we are interested in, for example here, that looks like 1.7, and we are interested in predicting the y coordinate. Now you're probably thinking, man, I don't care about your 2D lines here. Show me the cool stuff. Show me video generation, show me image generation, show me GPT style-like architectures, and I hear what you're saying, but trust me, I simplified these things for a reason, and that reason is it will be the easiest for us to actually understand how these models are implemented under the hood and to develop our intuitions here. But trust me, whatever we're going to learn here will actually generalize to all these more complex models and architectures very easily. So just to go over the basics, and then we'll return back to implementing our neural network model library from scratch. And then later on, we actually will implement some of these complex model architectures and train them that I just mentioned. So let's get back to our problem for a moment. We are given the x coordinate, and we want to predict the corresponding y coordinate for that input. Now, notice that without getting some more information about the task that we are working on, getting some more specification about the problem, this problem statement that I just described is kind of meaningless, right? Because as far as we know, with the information we've been provided so far, the ground truth y coordinate can be anywhere on the y-axis, right? So from positive infinity to negative infinity and anywhere in between. And you will see that this is actually a common theme for these optimization-based approaches, for the approaches that learn some value of parameters. So typically, what people do is they collect a data set of observations. Now, let's say these black points represent our data. That is, we went in the real world and collected some observations, as well as their ground truth labels from some process in the real world. So that can be any task that we care about, and we just plotted these observations in 2D space, right here on the plot. Now, you might be thinking, well, why do we need to care about training some model to achieve this task, right? To predict the y for this point, because, well, we already see the data, right? We can kind of guess that the correct label for y is somewhere here, right? Let's say 1.6-ish looks like, right here. Now, to illustrate why we can't just look at our data and figure out what is the correct label for a given input, let's go back to illustrate this. Let's go back to our previous image of the cat that we had discussed previously. So an image is represented in computer memory as basically just as a grid of values. So at each location in the image, there is some value associated with the brightness of the pixel in that location of the image. Now also, because this particular image is colored, so you can see that the objects here are not black and white, therefore this image, we need to store some additional information, right? So that is, for each location in the pixel, we need to store color values for red, green, and blue channels. For each pixel in the image. Now let's think, how can we visualize that image? Or even to simplify, how can we visualize a single pixel from that image? For example, the one that I just highlighted here. Well, because we know that each pixel has these 3 values associated with it, we might consider plotting it in 3 dimensions. So there will be 1 dimension for the green channel, 1 dimension for the red channel, and 1 dimension for the blue channel. And somewhere along these axes, this particular point that we're talking about here, it will lie, for example, right here, right? I'm just completely guessing at this point. Realize what we've been able to do is just to plot a single pixel, but our image is much larger than that, right? So now let's say our image has some height and width to it. Let's simplify and say both of them are 100, so 100 pixel tall, 100 pixel wide. Now, how can we plot this image? And how many dimensions do we need to plot this image as a single point, for example? Well, we have 100 by 100 pixels, and 3 values associated with each pixel. That corresponds roughly to 30,000. That's the dimensionality of space that we need to plot this image as a single point. Now, of course, this is very problematic for us humans who can only perceive things in 3 dimensions, right? So we have no hope of actually plotting our image in such a high-dimensional space. And this is actually the common theme. This is the case in general. Our inputs generally can't be plotted directly in this low-dimensional space. Right, so this was a tangent to our discussion here, and this is the explanation why, in general, we can't just plot our data as I have here and then look at our x-axis to guess the correct value of the y-axis. That's because, in general, again, we can't plot our input because it's too high-dimensional for us to perceive. So we're really going to want to stick to these optimization approaches. We want to define a model and make it automatically adjust its parameters to correctly predict the label. Now, to do this, you can notice that we're going to need some metric to estimate model's performance, to quantify how good or bad a given model's prediction is, so that intuitively it can have a signal in kind of what direction to improve its prediction. And essentially, this metric for how good or bad a given model prediction is called a loss function. By now, we mentioned the word model a couple of times, but we haven't yet discussed what it is. For now, I want you to have a very high-level understanding of it, and don't worry, we're going to unravel all of it. We're going to look under the curtains, we'll figure out exactly how these models implemented and what techniques are used to train these models. You're going to implement it yourself from scratch along with me, so don't worry. We're going to cover all of these implementation details just in a moment, but for now, the most useful thing would be is to have a very coarse, high-level understanding of the model, and we will unravel it gradually. So I want you to think about a model as a box, which is presented with some value, with an input, and the box returns us another value, which is a prediction. So the box does some computation and returns a prediction. Now, what this prediction is? Well, the prediction is the model's best guess or best estimate for the ground truth label, right? So you may notice that along with the input, we also have a label. But because there is no connection from the label to the model does not see the label. Instead, it only sees the input, and without knowing what the actual label is, the model is trying to predict or make the best guess of what the actual label is. Now, let's discuss exactly what the inputs and the labels are for the example that we discussed earlier, meaning this plot. Well, the inputs are the coordinates of points along the x-axis, and the labels are coordinates of the same points along the y-axis. So let's go a little bit slower here and discuss one point at a time. So we're not talking about all the points in aggregate, rather we're just focusing on one particular point highlighted in red. So for that particular point, the input right here, what the model will see, will be its x-coordinate of this point, meaning this value. And the label, in other words, the ground truth label for that point, would be the coordinates of the same point along the y-axis, meaning this value right here. So, for that specific training example, or in other words, this specific point, we're going to input 1.7 to the model, and we want the model to predict 2 right here. Now, this point that we discussed is only one training example for the model. In other words, it's just a single sample from our dataset. So our dataset contains all of these points, all of them, and each point individually represents a single training example. In other words, a single pair of the input to the model and the ground truth label that the model needs to predict. How are we going to make the model to predict the labels correctly? Well, on a very high level, for each prediction that the model outputs, the model wants to have some signal as to how good or bad that particular prediction was. In other words, what is the discrepancy between the actual label that this input has right? What's the discrepancy between the actual label and the model's prediction? Intuitively, you can think of it as model wants to know how good or bad its estimate of the label was, so that in the future, hopefully, the model can slightly adjust itself so that when next time it's presented with the same input right here, now it predicts something which is closer to the label. In other words, the model wants to minimize that discrepancy that I highlighted. It wants to make it smaller. Well, intuitively, it makes sense to us what a better or worse prediction is. So let's go back to our plot, and we're still talking about this point lying at this coordinate on the x-axis. So we're talking about this point right here, which has ground truth y value of 2. And let's imagine two possible predictions from the model and visualize them on the same plot. So let's say this is a possible prediction from the model number 1, and this is possible prediction from the model number 2. And let me quickly label them so we don't get lost. And by looking at this, of course, it makes sense to us that the prediction number 1 is better. And intuitively, it makes sense to us because the y value for the prediction number 1 is closer to the y value of the actual data point. But this intuitive understanding is not enough. We need to actually numerically quantify how bad or good a given prediction is, as to give the model basically some signal of how to improve its predictions in order to be closer to the correct value. And this is called a loss function. One way how we can easily quantify our intuitions here is to realize that if we go to the y-axis for each of our predicted points, and let's say the y value for the prediction number 1 is something like 1.9, and the y value for the prediction number 2 is 1.0. So our first attempt at a loss function for this case can simply be the difference between the correct y value for a particular point, highlighted in red, in our plot right here, minus the predicted y value for the same point. In other words, our loss function potentially can be a simple difference between the two. And to verify that it all works, let's just plug the y values for the two predictions, the two blue points that you see on the plot, into this formula as to get an exact numeric estimate of how good or bad a given prediction is. So for the prediction number 1, we get 2 minus 1.9, which is of course equal to 0.1. And for the prediction separately, for the prediction number 2, we get 2 minus 1.0, which is of course 1.0. Now we got the exact numeric estimates, but also they seem to conform with our intuitions. That is, the loss value for the prediction number 1 is lower or better than the loss value for the prediction number 2. So let's just clarify that. So lower loss is better and higher loss is worse. So the task of our models will be to minimize that metric. In other words, make the predictions closer to the actual ground truth labels. It turns out there is a problem with our previous loss formulation, and to illustrate why, I expanded the plot on the y-axis. So consider these two different predictions, highlighted in blue here. Let me annotate them as previously. So this prediction number 1, prediction number 2. For each of them, if we go to the value on the y-axis, and we try to plug them in the same formula that we defined above, so the correct y value minus the predicted y value, let's try to do this. For the prediction number 1, we will get 2 minus 5, which will be equal to minus 3. And for the prediction 2, we get 2 minus negative 1, which is equal to positive 3, because the negative signs cancel out. Now, you see that this seems to break the assumptions that we made previously. They seem to kind of hack our loss functions in an undesired way. Specifically, previously we defined that a lower loss value is better. However, for this case right here, even though the two predictions are of the same distance from the actual correct label, as you can see, the loss value for the prediction number 1 is much lower than the loss value for the prediction number 2. So we need to modify our loss function to account for that. One way would be to simply disregard whatever sign we got as a result of our computation. So instead of taking the simple difference between the ground truth label and the predicted label, we can take an absolute difference. And this can be our new loss function. if we plug these values, if we plug the same predictions into our new loss function, we will not get this undesired behavior anymore. And we still notice that we still preserve our semantics that we defined earlier. That is, a lower loss value corresponds to a better prediction, while the higher loss value corresponds to a worse prediction. This is good, right? Because the two of our predictions are indeed of the same distance from the ground truth point. And now our modified loss function actually does treat them the same. In other words, it assigns the same measure of goodness to both of them, and that measure of goodness sort of roughly corresponds to our intuitions, or what we as humans would perceive kind of as good or bad prediction for that use case. Now notice that our modification to the loss function actually did not change the semantics of this loss function. Specifically, the lower loss value still corresponds to a better prediction, while the higher loss value corresponds to a worse prediction. In other words, a greater distance between the predicted point and the actual ground truth point. Now, this is not always the case, right? You can totally imagine a different modification to the loss function that would completely change these semantics that we defined here. And therefore, we must always be vigilant and very careful whenever we kind of fiddle with our loss functions, because this has a direct effect on the optimization objective. In other words, it directly changes what the model optimizes for. Now, this is a very important takeaway that generalizes to any deep learning problem that you're trying to solve. A neural network does not look at a particular problem you're solving from our human perspective. It does not have our human intuitions or does not have a common sense about a problem. Instead, it fully relies on this loss function that we defined. It fully trusts that numeric estimate of how a given prediction is good or bad. If our loss function does not fully capture our human intuitions about a particular problem, the neural network will not know this. Instead, it will just blindly optimize for whatever the loss objective says is a better prediction. And this example of us actually needing to adjust our loss function because we observed that it doesn't fully capture our human intuitions about a particular problem is a prime example of that. Let's actually describe what a model is. Previously, we spoke of a model as being a black box, but now I want to basically gradually unravel that abstraction and look exactly how a model can be implemented. What do we mean when we say a model? Well, typically, we mean a model of our data. And what data are we modeling? Well, it depends on the task. For the problem that we discussed previously, meaning predicting y coordinates from x coordinates, our data was all these points right here. For some different task, for example, autonomous driving or image classification, the data can be different. But typically in the field of deep learning, people talk about models abstractly as being a model of whatever data they are interested in. And in the field of deep learning, you will typically hear people using words deep neural network as being interchangeable with the word model. But it's important to note that not necessarily every single model of data is a deep neural network. For example, just now, we're going to start with a very primitive model of the data, which is not a neural network, and gradually we will add complexity to that model until it becomes actually a full-fledged neural network. So it's important to make that distinction here. Now, let's actually see how a very simple model can be implemented. And just as before, we are given some input to our model. Our model performs some computations. Here I'm drawing cogs, as in there is some machinery that implements the computation. And as a result of this computation, we get out a prediction. There's almost an unlimited number of ways how one can implement this machinery in the middle, but for now, we're going to focus on a very simple model. And gradually, we will add complexity to that model. We'll make it more and more sophisticated until it actually becomes a multi-layered neural network. For now, we're going to stick with a very simple model indeed. My reasoning behind introducing the topic this way is that each step along the way, meaning each step that we're going to improve our model, you're going to learn something very valuable from the first principles. That is, we're going to face some bottleneck in our previous implementation that we're going to need to adjust in our new implementation, which result in some valuable takeaway, which is difficult to achieve otherwise. If I just told you how people currently do deep learning, you will not acquire kind of this valuable takeaways along the way. That is, you will not gain kind of an intuitive understanding of the topic. And that's what I want to teach you in the first place. Let us actually proceed to our first implementation of a model. Let me actually denote that this is our implementation number 1. And here our model is extremely simple. So our model has only a single parameter. We'll discuss this in a moment. Don't worry about this. Our model receives an input, just as we had before. And the computation that our model performs, which is equivalent to this set of cogs right here, is simply a multiplication of the parameter with the input, which results in the model's prediction. Now notice that we have something new here that we didn't discuss before, and this is this parameter. What exactly is it? Well, think of it as being some internal state that the model has and has control over. So this parameter is not received by the model as part of the input, so it is not part of our data set. Instead, this is some internal variable of the model that the model can slightly adjust as to make its prediction closer to the actual ground truth label for that particular input. And again, remember that the closeness of the prediction with the label is not some abstract value. Rather, this is an exact numeric quantity which is defined by the loss function. For our task, the loss function that we defined earlier right here. Yeah, so it's a simple absolute difference between the correct label and the model's prediction. So given that measure of kind of how good a model's prediction is, and given the fact that the model has its parameter, the model basically can adjust its parameter as to bring its prediction closer to the correct label, according to the loss function that we discussed above. For now, don't worry how exactly the model is able to adjust its parameter as to bring its prediction closer to the actual label. We'll discuss that algorithm in great detail a little bit later in this video. Let us actually think from the first principles and develop our own intuitions as to how this algorithm might look like. As we will learn a little bit later, our attempts will not be exactly efficient or preferable to the actual algorithm which is used in this case, but nevertheless these are very useful attempts because they will help to strengthen our intuition. So we'll discuss that efficient algorithm a little bit later, but for now let us actually develop our own intuitions and make our first attempts as to how this algorithm might look like. Perhaps the simplest algorithm that comes to mind is we can just pick this value for the parameter randomly. So in deep learning, word parameter is used interchangeably with the word weight. So that's why I used lowercase w here to stand for the weight, in other words, the parameter, which is the same thing. The more important thing here is that I picked the setting for our parameter randomly on the horizontal axis, and just by chance, it turned out to be 1.5 approximately. Then I took that value, I plugged that into our model in place of this parameter right here. I took some point from our data set, I took its x-coordinate, fed it to the model right here. The model performed the computation by taking that input and just simply multiplying it with that parameter, which resulted in its prediction. Then I took the prediction and the actual label for that input and plugged it into our loss function right here, which resulted in the loss value for that particular setting of the parameter. And then you can think of it as I did it not only for a single data point in our data set, so not only for that point, or this point, or that other different point, but rather I did it for every single point in our data set, calculated its loss value, given our setting of the parameter and given our model right here, get loss value for every data point in the data set, and keep in mind what the loss value tells us. It simply tells us the difference between the model's prediction for a particular data point and the ground truth label for the same data point, right? So it's kind of simply the discrepancy between the two, according to the loss function that we defined. And imagine that this procedure was repeated for every single data point in the data set, and these losses for every data point were averaged out. So the loss here is not for a single data point, but rather for the entire data set that we have for all our points combined, which resulted in this value, 3, that I plotted on this 2D plot, right? Because I acquired this average loss value with this setting of the parameter, w. Therefore, I plotted on this x-coordinate, right? So you can hopefully roughly see what this plot is trying to tell us. Notice that these axes of setting of the parameter versus the loss value are completely different from what we discussed previously. Previously, we plotted just the xy coordinates of each point, whereas now this is also a 2D plot, but the axes stand for completely different things, so I just wanted to make this distinction very clear to you. Now remember, our objective here is to find such a setting of our parameter so that when it's used inside our model right here, this will result generally in a lower loss across all of our data samples. In other words, we want to find such a setting for the parameter as to minimize the average total loss for all the samples in our dataset. So is that setting for the weight or the parameter that we just tried is good enough? Well, so far we don't know, right? Because we haven't tried any other setting for the parameter to compare against. Well, let's say actually we went ahead and did this. So say we started from this setting for the value of our parameter that we discussed earlier, that we got randomly, and then we simply went to the right along the horizontal axis in regular intervals, and each time we tried a new setting for our parameter and repeated all of the steps above, which each time resulted in a different value for the average loss for all the samples in our dataset, which I visualized here along the y-axis. So you see the values here are different for each of the setting of the parameter. Each point lies kind of on a different altitude along the vertical axis. This is an illustrative example, so I actually did not take these values for the parameter and did not plug them into these formulas above. So the actual values along the horizontal axis might be different, but the general concept that I'm illustrating here holds regardless of these exact values for this specific problem and the model that we are discussing. The exact values here don't matter for the purpose of building the intuition, because the actual concept that I'm describing is bigger than this specific problem or the model that we're discussing. So let's just assume for now that these values indeed come from our model and our dataset. Now, if we connect the points that we got with lines, you can see that we get something like this. This is pretty coarse. But if we try enough settings of the parameter, we can get a more fine-grained plot like this. Again, this is an illustrative example. What does this plot tell us? Well, remember, our goal is to find the setting of the parameter as to minimize the loss. And here, we roughly achieve the minimal loss at this point right here. So we are interested in the setting of the parameter w, or our weight, or in other words, our parameter, which is located on the horizontal axis. So with this setting of the parameter right here, we get the best possible loss, at least from the ones that we tried. So this setting of the parameter gives the best predictions from our model. In reality, people do not use this algorithm for stepping in regular intervals to find the optimal setting for the parameters of neural networks, and also people do not use random search for that reason. And why exactly this is not done? Well, hold this thought for a moment. We'll return to it shortly. I guess one question that can arise is that, well, why did we need to go through this entire process of trying different settings for our parameter if we can just look at this plot and visually see that the best loss achieved here, so the best setting for the parameter is right here? Well, that's because you don't know the shape of this plot until you tried different values for the parameters, right? Because in general, when we just started right here, right, a few steps before, we only tried one value for our parameter, but we didn't know how the loss landscape, and this is called a loss landscape, looks beyond our point, right? In fact, it can have like arbitrary shapes in general, and you cannot know them in advance because of how complex your model is, that we'll go in a moment, how different is the loss function, right? So the loss landscape can have arbitrary shapes here. And until you tried different settings for the parameters, you just don't know, right? It just so happens that in our example right here, that value for the parameter was the most optimal one. But imagine a different loss landscape, which looks something like this, right? In this case, our setting for the parameter that we found approximately here is not optimal anymore, right? Because there is another setting for the parameter that achieves even lower loss, right? So the difference between this point and this point on the y-axis is significant. So the answer is, in general, you don't know how the loss landscape looks until you tried at least some combination for the parameters. And if some things are unclear, don't worry, we'll go into even more details a little bit later. Admittedly, this is a naive approach that has many disadvantages, but one of them is, remember that we went from the left to the right along the horizontal axis and tried different settings for the parameter. But now, once we know the entire kind of loss landscape, we know that this portion of the graph is essentially a wasted computation, right? So we did try different values for our parameters, but it did not result in a lower loss, right? It just resulted in ever-increasing loss. So we did not achieve a better setting for the parameter while we were going to the right after this point. But we still wasted a lot of computations here, right? So we needed to redo all these steps of plugging the parameter into our model, getting the loss function, getting the loss value from the loss function, repeating it for all the points in our dataset. And we needed to do this many, many times, right? Because to get plot of such a granularity as we have here, we needed our steps to be indeed very small, right? So the steps that we performed are very, very small. And this entire computation is basically a wasted effort. Let's describe our progress so far. First of all, we defined our problem as an optimization-based approach. So as opposed to writing a solution to a particular problem by hand, instead we will use a learning algorithm that will essentially tweak or adjust its parameters in such a way as to correctly and accurately predict the actual ground truth label. Then we defined a notion of a loss function to numerically exactly quantify how bad or good a given model's prediction is. Intuitively, this will give our model some signal as to in which direction to improve its prediction to be closer to the ground truth value. Then, we spoke about what the model actually means. First of all, we discussed it as a simple black box, but then we actually made our first implementation, which simply consists of one parameter and which simply consists of a single parameter, and it multiplies this parameter with the input that is given, which results in the model's prediction. Then we defined an algorithm to automatically adjust this parameter of the model as to minimize model's error in its prediction, in other words, to minimize the loss. Essentially, our optimization algorithm so far is to tweak the parameter of our model and to see its effect on the loss value by taking in that parameter and some sampled input and feeding it through the model, getting out the prediction from the model, and feeding that prediction to our loss function, which results in a loss value. So the real neural networks do not actually optimize their parameters in this way, and it may not sound like a big problem to you at the moment. However, I want you to intuitively understand why the neural networks in the real world, for them, it's actually prohibitively expensive to perform optimization of their parameters in this way. To understand why we want to make improvement to our algorithm for modifying the model's parameter to get a lower loss value, let's make a change to our model and let's actually make it a little bit more advanced. You will see that it will actually lead us to some conclusion that generalizes beyond this toy model that we are discussing here and actually applies in general in the field of deep learning. So our implementation number 2, let me denote it here, will have not one, but 2 model parameters. Let us discuss our reasoning behind adding the second parameter to our model, but first, let's go over the exact mathematical computation that our model performs. The model still receives an input and performs a multiplication of its first parameter with that input. Well, this is exactly what we had previously in our implementation number 1, but then, and what's new, this computation is, let's say, added to the second model parameter, which results in the model's prediction. So in general, our reasoning behind adding more parameters to our models is that it increases their representational power. In other words, it gives the model more freedom to represent more complex things. In other words, it sort of broadens the range of the outputs that the model is able to perform. A little bit more concretely, imagine that for some simpler learning task, the second parameter is not, and the associated computation is not actually very useful. In this case, the model can simply learn to set this parameter to 0. In this case, this part simply will cancel out, and we are back to the model architecture that we have previously. But imagine for some presumably more complex learning task, the second parameter is actually useful. In other words, setting that parameter does actually help the model to drive the loss value down as guided by the loss function. In that case, the model presumably can learn to adjust the second parameter to additionally decrease the loss value, which results in a better model prediction. So you can see that our second implementation is strictly more general than our first implementation, and that's because the optimization algorithm can learn how to optimally use all of our provided parameters as to achieve a more minimal loss. So at least the second parameter does not hurt our model, right? And if anything, it helps our model to achieve even a lower loss value, that is, to achieve a better model prediction. That's because our model is able to perform all the computations that our previous model was able to perform, but now, in addition, it can optionally make use of its second parameter, depending on the task at the hand. Now, let's go back to the problem that I raised earlier, to illustrate why we might want a better algorithm for finding the values of our parameters as to minimize the loss value, consider the case where we have not one, but two model parameters. And the intuitions that we're going to develop here will work for any model, and in fact any neural network that has multiple parameters, and not only for our specific setting that we have right here. So this is exactly a similar problem as we had before for the model with one parameter. The only difference is that now we have two. So instead of having a two-dimensional plot, where we visualize the setting of one parameter with respect to the loss value, here we have two parameters, so the plot is three-dimensional. But the semantics are exactly the same. So we're interested in finding the setting of the parameters as to when these parameters are plugged in place of these values right here, and some input is presented to our model, we want the resulting prediction to be close to the ground truth value for that input. In other words, we want the loss value to be low for these settings of the model parameters. So we're interested in finding the model parameters that minimize the loss value. What happens when we try to use the same exact optimization algorithm that we used to train the model that only had one parameter? That is, somewhere in the space of parameters, we pick a point. Let's say we happen to select this point right here, which corresponds to us just by chance selecting value 2 as the setting of the parameter number 1 of our model, and value 1 as the setting for the parameter number 2 of our model. Then we take these values for the parameters, we plug them in place of these boxes right here. Then we evaluate the resulting model with this setting of the parameters on some input. We get the model prediction, we plug the model prediction into the loss function, we get out the loss value as a result, and let's say we repeat the same procedure on all the data points in our dataset, and we simply averaged out their loss values to get out, a combined loss value for the entire dataset, and we plot the resulting average loss value somewhere on the vertical axis right here. So this corresponds to kind of a measure of goodness of the model's prediction on our entire dataset with these settings of the parameters that we chose. Exactly as before, we are interested in finding such setting for these parameters that minimizes loss value the most. In other words, as to improve the model's prediction as much as possible, let's say we go around in the space of parameters in regular sized intervals in order to try to discover a better combination of these parameters that minimize the loss even more. So let's say just by chance again, our optimization algorithm happened to try out this point right here, which again corresponds to this setting for our parameters. So let's say weight parameter number 1 happens to have value 1.5 in this case, and parameter number 2 happens to have value 3. Now we repeat the same procedure as before, and we get out the loss value that we again plot on the vertical axis in this figure, let's say right here. This was intended to illustrate that we would prefer the second setting of our parameters because it resulted in a lower loss value. And let's say we go around in the space of parameters, continue our exploration in, let's say, regular-sized intervals in each direction. Now I want to clarify that this is an illustrative example, so I want to develop your intuitions about optimizing models with multiple parameters in general, so these are not tied to the exact use cases that we discussed earlier. So if we try this process of exploring in the space of parameters and plotting the loss values enough times, we can expect to get something like this. Do you see the problem here? Well, to cover the space with the same density of samples, stepping in regular-sized intervals, as opposed to the model that has only one parameter that we optimized before, here we need to try out exponentially more settings of the parameters as the number of parameters increases. Now, and don't be confused that you can just select the most optimal setting of these parameters by just looking at this plot, because, again, as we mentioned before, generally you don't know how the loss landscape looks like until you have went around and tried different settings of these parameters. So it is not the case that we can just directly know that this is the most optimal settings of our model parameters. We only can get to this value by exploring the space around until we have gotten lucky and found the one that minimizes the loss the most. In general, as we discussed earlier, you do not know in advance how the loss landscape of a particular model for a particular optimization task looks like. So we can only get, in other words, we can only get to this point by searching and exploring around, stepping in different directions until we get lucky and stepped right here. Now, we know that this results in a low loss value, but we do not know this in advance, that is before we tried other settings of the model parameters, unless we of course get very lucky and just happen to start with this point in the beginning, which is generally unlikely, because there is many more other points where you can end up by chance instead of that point right here. To be more specific, previously when we optimized the model that had only one trainable parameter, we tried out 4 different values for that parameter. To achieve the same density of samples with our new model that has not one but two trainable parameters, we need 4 to the power of 2, which is 16 samples. And intuitively, that makes sense, because imagine on this plot we have only a single trainable parameter, and we sample 4 values along that dimension, which is exactly what we did previously. Now, because our modified model has 2 parameters, and we want to achieve the same density of samples, in other words, we want to try out kind of the same amount of different settings of our parameters in the 2-dimensional case. Therefore, we also need to sample 4 values in that dimension as well. Right? Another way how to kind of intuitively understand this, when we are tuning the parameter number 2, we keep the parameter number 1 fixed. In other words, you see that when we are perturbing this parameter, parameter number 1 does not change. And the same goes for the parameter number 1 when we adjust its value along the dimension, parameter number 2 stays fixed. And that's maybe to disentangle the influence of each of these parameters on each other, right? So we're perturbing only one at a time while keeping the other one fixed. So when we fill out the missing points on the plot, sampling 4 times in each dimension, this results in 16 samples. And the general takeaway here is that to achieve the same density of samples in a higher dimensional space, we need the number of samples which is exponential in the dimensionality of that space. So more concretely, the 2 here stands for the number of trainable parameters that the model has, so that's the dimensionality of our space, and the number 4 here stands for the density of our samples, which I set to 4 because that's the number of tries that we used when we optimized our previous model that only had 1 parameter. So we can try to generalize it even further. Imagine that our model has 3 parameters, in which case the number of tries, if we want to achieve the same density of samples, would be 4 to the power of 3, which is 64 samples. And you see that it gets out of hand very quickly. Now, the real-world models have hundreds and thousands, millions, sometimes billions of more parameters. So you can see that this number gets truly astronomical. As an example, imagine that we want to try out 10 different values for each of the parameters in a model that has 3 parameters overall. That would result in needing 1,000 samples. Now imagine that we changed our model to now have 6 parameters, which would correspond to needing 1 million samples. Now, the real-world neural networks have hundreds of thousands, sometimes millions or billions parameters, so this number becomes truly astronomical there. For comparison, the number of elementary particles in the universe is 10 to the 86. That really shows a necessity of adjusting our optimization algorithm to generalize to a higher dimensional space, to the model that have more trainable parameters, because there we cannot just search in regular intervals, as we did before. And so that's what the real neural networks do in practice. They implement an optimization to that algorithm that we discussed earlier, and now we're going to go exactly in details of what that optimization to the algorithm is. So that really necessitates the changing our algorithm for modifying or adjusting our model's parameters to achieve a low loss value. In other words, we want to generalize that algorithm that we have been discussing throughout to now apply it to models that have multiple parameters. Now, one separate independent observation before we move on. Notice that it's not possible to visualize the loss landscape for more than 2 parameters in the same plot. Here we have 2 parameters, and our loss landscape is already 3-dimensional, right? So that's each of the parameters that we have has a separate dimension, and the loss value is this vertical axis. Now, if we imagine our model has 3 or more parameters, that would be impossible for us to directly visualize the loss landscape of all of the parameters at once, right? Because we can only plot and visualize maximum 3 dimensions. We can perceive as humans only the 3-dimensional space, so we cannot visualize 4 or higher dimensional space. We saw that the overarching disadvantage with our current approach is the fact that we are exploring the space blindly. That is, when we are at a point in our loss landscape, let's say right here, we don't have a signal as to in what direction to adjust our parameters, these values on the horizontal axis, to see the loss decrease. And remember, the loss value tells us how good or bad model predictions are with that particular setting of the model parameters. Keep in mind that we defined our loss function in such a way to mean that the lower loss value corresponds to a better model predictions. Remember that we use this formula to define our loss function. Please feel free to pause the video now and go back to the part of the current video where we discussed defining loss functions and about the semantics of them. But in short, that's the reason why we want to find such setting of the model parameters that minimize the loss, because lower loss means better model predictions. But because we didn't have that signal as to in what direction to adjust our parameters to see the loss decrease, we needed to exhaustively try out adjusting our parameters in all possible directions. And each direction, each yellow arrow here corresponds to trying out some new setting of the model parameters. So let's say this orange point corresponds to approximately these values for the two of our parameters. That another point corresponds to yet another setting of our model parameters. And essentially, because we didn't know in advance which one of the directions will decrease the loss, we needed to try out all these directions. And that resulted in us wasting a lot of computations on exploring the parts of the loss landscape that did not result in decreasing the loss value. So we did spend our computations on them, all these red points with a black cross on them, but trying out these parameters, the setting of the parameters, did not end up decreasing the loss value. So instead, if we somehow knew for this particular point that we are at, if we somehow knew which direction, which of these yellow directions decreases loss the most, let's say that for this particular point, it will be this green arrow right here, then we can explore the loss landscape in a more targeted way, right? We can just focus our computations only on that arrow without us needing to go around and try out all these other directions in the search space. So you can see that this can result in a way more efficient algorithm, especially as we go in higher and higher dimensions. In other words, as our models have more and more parameters in them. So more concretely, let's say we start with these settings for our parameter. So that's the value for our parameter number 1, and that's the value for our parameter number 2. And we take the values for these parameters and we plug them inside our model. That is, we use the settings of the parameters in place of these green boxes right there. And we execute or run our model on the entire data set of the points that we have. So we take each point and we feed to our model x coordinate of that point. And our model returns us the prediction for the y coordinates of that point. Right. Then we take the prediction of the model and with the ground truth label for each point and we feed it into our loss function right here, which results in some loss value, let's say here on the vertical axis. And that loss value corresponds to kind of the measure of goodness of the model's prediction, right? And we want to bring that value down. That is, we want to find such setting of the parameters that minimizes that loss value. In other words, the settings of the parameters which result in a better model prediction, right? You can revisit the notion of the loss function that we just discussed in this lesson, right? So please feel free to do so. But the notion is that we want to bring that value down. We want to minimize that loss. And so it will be very helpful if at each location, right, if we knew kind of the slope, the local slope of the loss landscape at that location, right? If we knew which way should we adjust our parameters to minimize the loss. For our three-dimensional case, the slope will be this 2D plane that is slicing through the space. You can imagine it this way. And just as a mental model, you can think of it as that point that we just discussed is located here in the loss landscape. And what we're trying to compute is this slope of the tiny little patch around that point, which shows the direction of the decrease and the increase of the function, right? Now, this is an illustrative example in the sense that in practice we cannot reasonably compute the shape of the entire loss landscape for high-dimensional problems, so we cannot actually visualize that plot. And the only thing that we can reasonably compute is the slope of this tiny little patch around that point, which I try to visualize here. And let's say the direction of the arrow here shows the direction of the greatest decrease of the function. Now, if we have this information, instead of trying out new setting of our model parameters basically all around that point, that's exactly what we did previously, which is inefficient. Now, if we know the direction of the greatest decrease, we can adjust our parameters in this targeted way. That is, we can change our parameters in the direction of the slope, right? And remember, we are doing this because we are interested in finding such setting of our model parameters that minimize the loss, because achieving a low loss corresponds to better model predictions, right? And so therefore, we're stepping in the direction of the decrease of the function, right? We're stepping to the lower loss value. So the new settings of our parameter will be, the old setting plus the slope at that location, which will result in these new settings for the model parameters. But then we can essentially repeat the procedure, right? We can try out that new combination of our model parameters, get a new loss value, and compute the slope at that new location in the loss landscape yet again. And here, let's say the thickness of arrows corresponds to steepness of the slope at that particular point. So because here the cyan arrow is thicker than the yellow arrow, that means that now at this new location in the loss landscape, wherever we are at, the slope is steeper, right? So the arrow is thicker. But again, we can adjust our weights in the direction of the slope, which would correspond, for example, to this new setting of our model parameters. again, we can compute the loss value with this particular combination of the model parameters, and we can compute the slope at that location yet again. Now you can see that repeatedly stepping into the direction of the slope, we managed to find a setting of the model parameters that were decreasing the loss at each step. So we started with this loss value on the vertical axis. As we stepped into the direction of the slope, we ended up decreasing our loss value, which is desirable again. And as we repeated the procedure, we ended up decreasing the loss value yet again, right? And so this is good. This means that we managed to find setting of the model parameters that achieve better model predictions. And so for illustration, if we had the knowledge of the entire loss landscape, that we don't have, in fact, right? That's purely for illustration. But our trajectory through the loss landscape would correspond to kind of this, approximately this path right here, right? So we firstly got to this point, then to this, and then thirdly, we got here. And so notice that without actually having the knowledge of the entire loss landscape, by repeatedly applying that rule for stepping down in the direction of the decrease of the function, we were indeed able to find the lowest spot in this landscape, which corresponds to a better setting of our model parameters. But notice that when we were at each location, we in fact did not have knowledge of the entire loss landscape, right? The only thing we knew is only the local slope. But by repeatedly following the local slope, we ended up in the global minima for this entire function, that is, in the lowest point for this entire function. Now, don't worry, I will guide you through implementing this new efficient optimization algorithm step by step in the moment. And so far, I just wanted to provide you with this intuition, with this mental model around that process, and we will jump into actually implementing this in code very shortly. There's a couple interesting things about this optimization process that I want you to notice. The first one is the initial value for our weights, that is, these numbers right here that we started our optimization with, can be important in the sense that if we were instead to use different settings of our initial model parameters, so instead of starting right here, what we just discussed, what if we chose these settings of the model parameters as our initial values, right? So approximately, let's go to the horizontal axis and draw what values of the weights these would correspond to, let's say approximately these values for our parameters, right? Then our algorithm would start from this location right here. And in this case, the optimization process would likely have taken us through this path, through the loss landscape. Now you see that kind of this path is different from the path that we previously saw, right? Just as a reminder, again, previously, this is the path through the loss landscape that we saw. So you see that these are different, right? And the exact trajectory through the loss landscape depends on the initial values of our model parameters. There is one more thing that I want you to notice, and that is depending on the initial value of our model parameters, the algorithm can actually end up in a different place in the loss landscape. More concretely, imagine for this third example, we're starting from this point right here. In other words, we start with the initial settings for, let's say, approximately this initial setting for our model parameters. So these values on the two axes. And that would roughly correspond to that point right here. Now, if our algorithm starts with this point, it would compute the local slope at that location, which would roughly correspond to, say, this region here. And our algorithm will then step into the direction of the slope, into the greatest decrease of the function, roughly in this direction, ending up in this location right here at that point. Now, if our algorithm then computes the local slope at that point, you can see that it's close to zero. In other words, there is no direction in which we can step that would decrease the loss value even more, right? Because you can see that kind of the surface of the plot in that spot, like it goes up, right? It does not decrease, rather the loss increases. It only increases from that point on, right? So if our algorithm ended up, in that spot, it can actually become stuck there and cannot escape that local optima there. It will end up with approximately, let's say, these settings for our model parameters as the final values for our optimization. Now, notice that these values on the horizontal axis for the two of our parameters in the blue points are completely different from the values for the model parameters that our algorithm discovered previously, starting from the different model parameters, right? So you can see that the red and the blue points on the horizontal axis are completely different, right? They're on the different locations. And moreover, if we go to the vertical axis for our previous solution, which would roughly correspond to this value of the loss, and now if we separately go to the vertical axis for our new solution, that would roughly correspond to this value of the loss. Now you can see that the blue settings of the model parameters achieves a higher loss compared to the red setting of the model parameters. In other words, the red settings, the red points for the model parameters achieve better model predictions, right? So, but again, if our algorithm were to start from this point right here, it would have like no hope but to, basically be stuck in this local region there, unable to kind of escape from that neighborhood there. And that would result in different final values that the algorithm will discover. Now, that may seem like a big problem, although in reality, when we are training neural networks, these models that have hundreds of thousands, sometimes millions or billions of parameters, this problem basically becomes pretty unlikely. And the reason why is that, remember that the condition for having this kind of optimization problem of being stuck in the local minima was the fact that there was no dimension in which, right, so there is no horizontal axis in which we can adjust our parameters that would decrease the loss even more, right? And that might be the case when we have only a couple of parameters, although in the high-dimensional problems, each parameter would correspond to some axis which the model can adjust the weight in that axis to potentially see the loss decreasing, right? And the more the parameter, so the more number of axes that a model can adjust, the likelier it becomes that there will be at least some parameter adjusting which would correspond to decreasing the overall loss value. That is to say that in the higher dimensions, when we're training the actual neural networks, this problem of being stuck in the local minima actually becomes pretty rare. By this point, you're already familiar with our implementation of the model. If not, please feel free to pause the video and go back to the part of the current video where we talked a lot about this implementation. And what you see right here is the same model, but visualized slightly differently. Specifically, these computational operations, these mathematical operations that our model performs, multiplication and addition, are now visualized or represented as these circles here, in other words, as nodes. And the connections between these nodes, for example, these arrows in our original implementation, correspond to these edges between the nodes. So this representation overall is called a computational graph. It consists of the nodes as these individual mathematical operations that our model performs, and the connection between these nodes correspond to the data flow through our model. Now, a little spoiler alert, we can actually implement a general script, a general function that takes in any arbitrary model that we implemented, including neural networks, and returns this representation of our model as computational graphs. And you're going to see in a moment why representing our models as these graphs is very convenient, at least on some level inside our deep learning library. Now, and the second thing that we discussed is this process for training our model, that is optimizing our model parameters. And we define that process as essentially traversal of some high-dimensional loss landscape. And our goal was to find such setting of the model parameters, these axes, that minimize this vertical value in the vertical axis, this loss value. In other words, our algorithm computed the local curvature of this landscape, standing at this point, and then based on that slope, we stepped into the direction of the greatest decrease of that function. Right? And by repeatedly doing that, we minimized this value here, the horizontal axis, which corresponded to our loss value, resulting in better and better model predictions. Now, what happens if we apply the same algorithm for this high-dimensional manifold traversal, for this high-dimensional landscape traversal, if we apply that algorithm directly to this computational graph right here, right? That is, what if our algorithm tries to minimize the model, the output of that graph, which is the model's prediction directly? Well, let's say I went ahead and actually did this. And don't worry, we're gonna go over step by step how exactly to implement this algorithm. Now I just want to provide a little bit more intuition before we go into the actual implementation in a moment. So bear with me. Let's just assume that I somehow applied that algorithm, and these are the resulting parameters that our algorithm found. So these are the weight number 1 and weight number 2. In other words, the parameter of our model number 1 and parameter number 2. Now, are these, and these are the final settings of these parameters that the algorithm discovered. Now, are these good settings of the model parameters or not? Well, it's really hard to tell abstractly, right? What in fact we can do to kind of test these parameters out is, well, we have our data, and let's say we sampled some point on the x-coordinate, let's say this point right here, and we want our model to predict its actual label. Let's say if the point were here in this blue circle, its y-coordinate would be approximately, let's say, 1.8. Now notice that, in fact, here there is no ground truth data point in our data set, but our entire assumption here is that if the model is trained well enough, in other words, if the model can accurately predict y label from the x coordinate for every point in our dataset, then if we feed some value which is not in the dataset but somewhere around these points, we want our algorithm to generalize. And if the setting of the weights is good, then our algorithm we would expect our algorithm to give this prediction, right, somewhere around that value. Now, what actually happens? Let's actually take these parameters that our algorithm come up with and plug it inside our model and feed that input to the model, and let's look at the actual prediction that our model returns us. Well, so these are the mathematical operations that our model performs, right? So this actually corresponds to our model architecture. In other words, to this computational graph that we just discussed, right? So the multiplication, the addition, these are exactly the same values that you see here. So the input gets multiplied with the parameter number 1, right? So the input is 2.5 and the parameter number 1 is minus 434. And the result of that computation gets added to the parameter number 2 right here, right? And so the overall prediction of our model, that is the output of this output of the model with that setting of the model parameters, is almost negative 16. Now, you see that this is very inaccurate prediction. In other words, our ground truth label in this case would be 1.8, but the actual model prediction is almost negative 16. Well, something clearly went wrong here, right? Now, if we can imagine the actual landscape that our algorithm traversed, it might look something like this. Now, you might notice that this is not actually the loss landscape that we used to see, right? Remember that this is our mental model for the loss landscape for that particular problem that we're discussing here. And we wanted to find that value, that setting of the model parameters, right, as we previously discussed. But the fact is that now our algorithm went or traversed a completely different function, in fact, right? So you see that these look very different. Now, our algorithm, because it again, no matter where it started, it always stepped into the direction of the greatest decrease of the function. So it was indeed optimal as to finding the settings of the model parameters that minimize this value on the vertical axis. So it indeed arrived to that point very quickly and efficiently. So these are, let's say, approximately the values of our parameters that the algorithm discovered. However, the problem is the vertical axis on that plot is not actually the loss, right? So, and what we wanted to minimize is the loss value specifically, because that will correspond to achieving a better model predictions. However, if we naively apply our optimization algorithm directly to the output of that computational graph, which is the model prediction, our algorithm, in fact, adjusted parameters in a way to minimize the prediction itself, right? So you see the vertical axis here is not the loss value, it's actually the model prediction itself. And that explains the weights, the final parameters, the final settings of our model parameters that our algorithm arrived at, these very negative values, because in fact they are purposely tuned by our algorithm to minimize the prediction as much as possible. So in fact, the more we train our algorithm, the more negative these values will become, right? Because it's our explicit objective of the algorithm at this point to drive the prediction of our model as negative as possible. I just wanted you to discover it for yourself that there was a bug in our implementation and that it is meaningless to directly train the model to minimize its prediction, right? Because it will result in these outputs which are not very useful. Now, so what we actually wanted our optimization algorithm to do is to find such setting of the model parameters that make the predictions of the model to be as close as possible to the actual ground truth label, right? So this right here was our implicit assumption. That's what we wanted our optimization algorithm to do. It'll be ideal if we can just take our model along with this high-level summary of what we want and just input it to some optimization algorithm and let it, find such setting of the parameters that satisfy our desire right here. Although in practice, this is not possible. We cannot say in words to optimization algorithm what we want, because this is not precise enough, right? This is too vague. What we actually need is an exact numeric estimate that tells our algorithm, this box right here, this box wants to know an exact numeric estimate that tells it how good or bad given model prediction is. And then it can use it as this value on the horizontal axis to minimize, right? So in fact, what we really wanted is we need this temporary component at the end of our model that quantifies goodness of the model prediction, where lower means better prediction. And so concretely this box, this is the loss function that we discussed so many times previously. This box contains human handcrafted knowledge for a particular task that sort of frame that optimization task, express it in a way where lower value means better prediction. We need to add that part to the end of our computational graph and then optimize that entire computational graph as a single function, right? If you go back and remember when we defined our loss function, remember our thinking process behind, right? That's what the formula that we ended up using for our loss function. But the way how we came up with that formula was basically to imagine, to go through our problem definition, through our data set of these points, and think through what would actually correspond to a better model prediction, what would correspond to a worse model prediction, right? And in general, for other problems and for other optimization, like deep learning problems, this loss formulation will be different, and it will depend on the task. But the exact sort of mathematical operations used here will essentially encode human knowledge about the subject, right? Because that's how we define our loss function here, and that's true in general. And so now, all of a sudden, you see that it does make sense now to use our algorithm to minimize the output of that computational graph overall, right, together with our loss function. Because now it has this nice defined semantics of, whatever we are minimizing here will actually correspond to better model predictions, right? So minimizing output of that circuit in the computational graph now corresponds to maximizing the quality of the predictions. And then, as we done with model training later on, we can just throw this part out, right? So we don't need this anymore after training. Typically, what we use our model for after training is just to get the model's predictions on some new input. So the actual value that we want after training is this here. So we can throw away, all of these computational operations after that part because we don't need this anymore, right? So, and we will still keep whatever model parameters our optimization algorithm found, right? So we'll keep the parameters and we'll remove the loss function because we don't need this anymore. And that, when we trained our model and then found out only after the fact that the optimization objective was not quite exactly what we wanted, I think this nicely illustrates some of the common problems that you might face when you actually go ahead and train the actual deep neural networks. Maybe the problems that you face will not be as severe as this one, like forgetting the loss function entirely. Although I think that does illustrate the point that sometimes we as humans, we trick ourselves into thinking that this optimization process inherently knows what we want and that it optimizes for that. But this is not the case, right? And as you saw, sometimes we can inadvertently introduce bugs into our optimization process. Imagine that our loss function was slightly incorrect, right? And in that case, the optimization process will still find that optimal trajectory through the loss landscape, getting to the bottom of that objective function. But if that objective function is not exactly mapping to what we would interpret as a better model prediction, then essentially the settings of the parameters that our optimization discovers will not be optimal, right? They will not be good enough as to our interpretation. And so therefore we should be vigilant and remember this going forward. Okay, so we framed our optimization process as this traversal of the high-dimensional loss landscape. And our algorithm relied on being able to compute a local slope at any point in that loss landscape. Previously, I sort of hand-waved that explanation away as to how our algorithm was precisely able to compute that slope. But now, let's actually look under the hood and go step by step and see how we can implement that algorithm exactly. So what the algorithm actually needed to compute is the slope of this loss value with respect to the two of our model parameters. So that, according to the slope, it can then modify the model's parameters to tune them or adjust them precisely in a way that would minimize the loss the most at that location. And if you remember our previous plots of the loss landscape, these three values actually formed axes of those plots. So the vertical axis was the loss value, and the two of the horizontal axes were our model parameters, or in other words, weights. So weight number 1 and weight number 2. So how can we go about computing the slope of this entire function? Well, one possible way forward is to realize that these three values in our computational graph are not actually connected directly to each other. Instead, there are all these mathematical operations in between them, sort of chained there. And we can actually isolate the problem and look and compute the slope of each of these mathematical operations one at a time, and then later on we'll be able to combine these into the slope of this entire graph, which is exactly what we want. So let's actually do that. Let's go step by step and consider the slope of each of these operations one at a time. You see that the first operation that our model consists of is this multiplication right here. So how can we compute the slope of the output with respect to the inputs for this operation, multiplication? And in general for other operations as well, right? Because there are also other operations in our graph later on. Well, one possible way forward is to use this limit definition of the derivative, and that definition may look complicated, although I assure you that this is actually very simple. Let's break this definition down and see exactly what this is telling us. Let me prepare a 2D plot so that we can visualize things. This will be the plot of the input to our function with respect to the output. And let's actually look at the formula. The formula tells us to take this function f right here, which in our case, because remember, we are only talking about this multiplication operation for now, as we discussed earlier, so this f will be the multiplication operation itself. Then the formula tells us to take some input to that function, this a right here, which corresponds to this, let's say this point on the input axis, right? Take some any input to that function, and then the formula tells us to evaluate our function on that input. In other words, feed that input to the function, which will result in some output, let's say this point on the output axis. And now, because we have this pair of coordinates corresponding to both of our axes, we can plot a point corresponding to the two of them. Then the formula tells us to take the same input, this a right here, which corresponds to this point on the input axis, but now adjust or perturb it by some margin, this h right here. So I'm denoting that h by this blue arrow here. And changing our original input results in some new input, let's say this point on the input axis. And then the formula tells us again to take our function, in our case multiplication operation, but now feed this new perturbed input to our multiplication operation, which will result in some different output, let's say this value right here. And as previously, we have this pair of coordinates, and we can plot a relationship between them. We can visualize it as a point in this 2D space, right? Then the formula tells us to subtract the two of the outputs of the function right here, which in our plot corresponds to this red vertical arrow. Then the formula simply divides that change in the vertical direction by the change in the horizontal direction. In other words, this. So the formula, what's really is computing is the change in the vertical direction divided by the change in the horizontal direction. So what's really is computing is the slope. In other words, the two evaluation of our functions resulted in this line through the space, and this definition is computing the slope of that line. Right here, you may notice that the step is, what this means is actually the step is very small. And the reason why this definition uses a very small step size is because this function, this definition of trying to compute the slope is trying to be general. And in practice, functions are not limited to be these lines, as we saw. In practice, these functions can be arbitrary nonlinear functions. And in this case, if we were to take a large step on the horizontal axis, right here, we would essentially be approximating this curve with a line, which is of course not correct, right? You see that they do not match. So in this case, the computational slope will be incorrect. So the way, and you see also that this is not meaningful to say that the slope of the curve, because the slope is changing along the curve, right? It's different depending on where we are at this function. And so the correct thing to do this is essentially approximate the curve with many small lines, essentially, and compute the slope at a very small step. So semantically, this is what definition tells us. Okay, so let's actually go ahead and simulate an optimization algorithm, which is called backpropagation, one step at a time, so that we understand exactly what this algorithm is doing. Now, there are two distinct phases to that algorithm, the forward pass of the model and the backward pass. For now, let's compute the forward pass of the model. Right? So it simply stands for computing the output of our graph, right, and recording any intermediate values, any intermediate outputs of our nodes, because these will be used later in the backward pass. But for now, let's only record these intermediate values, and we will use them later. So concretely, when our model has some defined setting of its parameters, and when our computational graph is presented with some concrete numeric input value, the graph will perform these mathematical operations that you see inside the graph, denoted as these circles, as these nodes. And what we need to do is we need to record outputs of each of these circles, right? And these are called intermediate outputs because most of the outputs of these nodes in the graph, they are not final outputs of the graph itself, right? Rather, they are some intermediate values that are later on used by other nodes to perform their computation in turn, right? So they sort of hang somewhere in between the nodes and are used as temporary sort of intermediate values when computing the final output of the graph, right? So for our algorithm to work, it will need to know these intermediate values. We simply pick values from our initial starting model parameters. In this case, let's say it's -1 for the parameter number 1 and 1 for the parameter number 2. Remember that we have our training data set of inputs to the model, and for each input we have the ground truth label, which is the value, the actual correct value which we want our model to predict. So let's say I went ahead and sampled some pair of input and the desired output to our model from our data set, right? And let's say I happen to sample input with value -2, which has its ground truth label value of 5. Again, we can get it from our data set. Now, what computations will our model perform, right? How do we compute these intermediate values, which are the outputs of each node in this graph? Well, we can just simulate the execution of our computational graph, right, by hand. So specifically, the first operation that the model will perform is it will multiply this -2 by -1. The result is +2. Let me go ahead and write down output of each node. And remember, we are doing this because our optimization algorithm for tuning the weights, it will require these values. So we need to record and keep track of these intermediate outputs of these nodes. The next operation that our model will perform is it will add 1 to the output of the previous node. So 2 plus 1, the output is 3. Let me write down. So it will be the output of this addition node in the graph. Then you see that the model essentially predicted the value of 3. Keep in mind, we discussed this already, but remember that this group of nodes semantically corresponds to our loss function, while this group of nodes corresponds to our model, right? So we see that the output of this addition operation, and please feel free to pause the video and go back and revisit this part of the current video where I went into details of the loss functions and why exactly did we add this latter group of nodes in our graph. Please feel free to pause and revisit that if you'd like. But you see that essentially our model predicted a value of 3 for this particular input, while the actual ground truth label for this node is 5. So we see that the model is incorrect in its prediction. And so we have this additional group of nodes which will be responsible for quantifying the error of the model, right? So which corresponds to our loss function, right? So the next operation that our model will perform is it will subtract 3 from 5, right? It will subtract the predicted label from the ground truth label of the model. Write it down as the output of the subtraction operation, and then it will take that. The final operation that our model performs is it takes absolute value of +2 in this case, which will be +2. Right? This absolute value, it would essentially semantically, it will kind of remove the negative sign of its input, right? If the input to that node was -2, the output would have been +2. But in this case, because the value input to this absolute value node is already positive, the output of this node is basically the same as its input, right? And so that's our final loss value, which is output from our graph. So let's actually go ahead and simulate our algorithm, which is called backpropagation, step by step. Now, in fact, our algorithm will, work for any neural network, right, no matter the size of it. So here we only have 4 operations, although the algorithm that we're going to describe right now will work for any arbitrary size model for thousands that can have thousands of operations. Okay, here I cleaned up our graph a little bit, and we can proceed to the more interesting part, and that is computing the slope of the output with respect to the model parameters, which is the numeric value that we need so that we can adjust our parameters in a way to minimize the loss the most. So that this will result in the efficient optimization algorithm, as we discussed earlier. Now, in fact, our backpropagation algorithm will start from the end of the graph, not from the beginning, and it will start with a value of 1. Now, semantically, you can think of it by remembering what's the final end result that we want. Well, the final quantity that we want to compute is essentially how much do our model parameters influence the final output of the graph, so that we can tune our parameters as to minimize that output of the graph the most, which would correspond to minimizing the loss value the most. And essentially, we to achieve that, we need to disentangle how much does each of these operations in the graph influences the final prediction, right? And we can do that by essentially assuming that the final node in the graph is fully responsible for the output, and then gradually sort of unwind that process and incorporate influences of all the other computational operations in our graph one by one into the final output of that graph, right? Until we reach the model parameters, right? So we start from the end, we assume that the final node is fully responsible for the output, and then we gradually go one operation at a time in the reverse order, sort of unwinding that process, and incorporate influences of each of these operations until we reach our model parameters. And by the time we reach our model parameters, we'll know exactly how much do these parameters influence the final output of the graph, right? So we'll be able to adjust our parameters to minimize the loss, which will in turn correspond to better quality of model predictions. Okay, so let's actually go ahead and mark that value as complete. So done. Now, the first operation that our backpropagation algorithm will see, going from the end of the graph, is this absolute value node right here. And we want to compute, if we change the input to that operation by some amount, how much will the output of that operation will change? In other words, we want to compute the slope of the output of that absolute value operation with respect to its input. So just as before, let's go ahead and consider slopes for this individual operation in isolation. Sort of let's for a moment forget that this operation is embedded into this larger computational graph and only focus on that operation alone. And here by this box right here, I denote that for now we're only focusing on that operation. Also, you may notice that I colored all of our nodes differently, and the color of this specific box actually corresponds to the color of the absolute value node in our graph, so they're both blue, and that's hopefully just to visually semantically separate that this box right here is only concerned with this absolute value node in the graph, right? So, and not with any other node in the graph, because we'll return to these other nodes later. But focusing on that operation for now, absolute value. Just as before, let's go ahead and use this definition of the derivative to compute these slopes. So according to the definition, we take some input value, let's say -3, and we feed it in to the current function, which is the absolute value in this case. And when feeding -3 to the absolute value, we get output of +3, this value right here. Then, following the definition of the derivative, we take that previous input, this -3, and we adjust it by some amount. Here I denote this by this blue arrow here. In this case, I change it by 2 units. So the previous input was -3, and the new input is -1. Now, in actuality, in the actual definition of the derivative, these perturbations are very small, as I explained previously, but for this example, our changes will still work. So, and this results in a new input, -1, and then we take that -1, and again, we feed it to our current function, which is the absolute value, and this results in a different output of +1, right? So notice the first input that we got was +3, and the second input that we got was +1. Now, the definition of the derivative tells us to subtract the two of these outputs. This will correspond to this change in the vertical direction as shown by this red arrow. Then, according to the definition, we need to divide the change in the vertical direction by the change in the horizontal direction. So what this definition, again, is computing is the slope. So another way to see this is the two of these points in our 2D plot, they form a line, and we want to compute the slope of that line. So we want to compute the change in the vertical direction divided by the change in the horizontal direction. So let's go ahead and plug these values in. So this change in the vertical direction, this red arrow here, is 3 minus 1, which is +2. And the change in the horizontal direction is -3 minus -1, which is -2. When we divide these values, we get our answer for the slope, which is -1. Let me clean up the plot. That's what we computed for our absolute value operation. The slope is constant and has a value of -1, so the slope is decreasing. And also keep in mind what the slope of -1 tells us. It tells that for this specific operation, the absolute value, if we change the input by some margin, the output of the circuit of this operation will react by decreasing by the same amount. That's what the slope of -1 means. But I want you to show another pair of inputs for the same operation. This will actually learn something very interesting about that. So let's go ahead and try out a different pair of inputs for the same operation. I will not go through all the computations here, but the calculation will proceed as before. We take some input, we feed it to our absolute value, we get the output, in this case +1, then we perturb our input, resulting in a new input, which has, in this case, let's say a value of 3. And again, we feed it to our absolute value, getting another output, value +3. In this case, because both of the inputs are positive, the absolute value does not change the sign, right, of the output. The output is the same as the input, in other words. Now, the definition of the derivative again tells us to subtract the two of the outputs. So this is 3 minus 1, which is 2. The change in the vertical direction is +2. And the change in the horizontal direction is also +2. So when we divide change in the vertical direction by the change in the horizontal direction, and we plug in the actual values, we get 2 divided by 2 equal to 1. In other words, the slope of that line right here, just as before these 2 points, they form a line, and the slope of that line is now +1. Let me clean up the plot one more time. And we actually see something interesting here, right? We see that this function is not a linear function. It is in fact piecewise linear, right? So we cannot describe the slope of that function with a single number, right? Because the slope is different depending on where we are in this function. Concretely, when the inputs to that function are negative, then the slope is -1. The slope is decreasing. Although if the inputs to that function are positive, then the slope is +1. So the slope is increasing. And keep in mind what the slope of 1 tells us. It says that if we change the input to that operation by some amount, by some margin, the output of this circuit, the output of this operation, will react by increasing by the same amount. Now, and just as before, we actually did not need to visualize all of that in practice. People use rules of calculus to derive these slopes, and this turns out to be even way more precise and accurate. I just wanted to provide some visual intuition for you. That's why we did these visualizations. And I organized things in such a way that, even when we didn't precisely use the definition of the derivative, because remember again, our step size or perturbation to the input was quite large, I sort of prearranged the things in such a way where our computation of slopes still turns out to be correct for this particular operation. Now, and one more thing I want you to draw attention to is for each particular operation, in this case, remember, this box sort of encapsulates calculations that are specific to only the absolute value node in the graph, but we only need to compute the slopes for each operation once. In this case, we computed the slopes for the absolute value node, and then every time we see the absolute value node in our graph, we can simply reuse these slopes that we computed. In other words, we don't need to recompute the slopes every time for each operation. Right? We only do it once, and then we can reuse this later. In practice, people don't visualize these things to compute the slopes. Instead, they use the rules of calculus to derive them. Now, let's go ahead and plug these values for the slopes that we just computed back into the larger computational graph. So this is the state of our graph that we left before zooming in to this particular operation, absolute value. And now let's actually return back and plug these values for the slopes that we just computed into that larger graph. Now, I want you to draw your attention that when we execute that model, when we computed the output of the graph, the input that was fed into this absolute value node here was a positive value. It was +2 here. So therefore, we are in the positive regime of that absolute value function where the slope is 1, right? So let me write it back here. The slope, as we just computed, is +1. Now, another way to see this, let's go back for a moment into inside our absolute value node, denoted by this box. And essentially, we are in this part of the function, right? So where the input is positive and the slope is +1, right? So for a moment, we ignore this part of the function where the slope is negative, because this does not apply to our case, right? This only applies when the input was negative, which is not our case. In our case, the input was positive, and the slope, corresponding slope, is +1. The slope of the output with respect to the change in the input for this absolute value operation that we just discussed. This slope is highlighted in blue. And then in addition to that, we previously computed the slope of the output with respect to itself, highlighted in red. Now, we want somehow to combine these together into the slope of this entire subcomputation. But currently, we have them sort of separated and not tied together. In other words, in our graph, we have some slopes that we already computed previously, so-called upstream slopes, if you will. And semantically, what they tell us is how much will the output of the entire graph will change if we slightly increase the output of the current operation that we are looking at. And if that value is positive, by the way, that value here is represented by this red arrow, and if that value is positive, if that upstream slope is positive, that means if we slightly increase the output of the current operation, the output of the entire graph will increase by some amount. Right? It will increase because the slope is positive in that case. And by what exactly amount the output of the entire graph will increase relative to the change that we apply to the current, to the output of the current operation? Well, that depends on the steepness of that slope. If that slope is very steep, that means if we just nudge the output of the current operation by a little bit, the output of the entire graph will increase by more than that, by multiples of that. And again, the exact quantity depends on the exact value for the steepness of the slope. On the other hand, if that upstream slope is negative, that means if we slightly increase the output of the current operation, the output of the entire graph will react by decreasing by some amount. In that case, it will decrease because the slope is negative. And similarly, by what exactly amount the output of the entire graph will decrease? Well, it depends on the steepness of that slope. And then separately, in addition to that, what we've just computed is the local slope for the given operation that we are looking at. And in that case, that operation was this absolute value node, as you might remember. So this node. And semantically, what this local slope is telling us, and by the way, that local slope here is highlighted by these blue arrows right here in the plot. And semantically, what this local slope is telling us is how much will the output of the current operation that we are looking at will change if we slightly increase the input to that operation. And you see that these two values, this local slope and the upstream slope, they represent sort of different semantic quantities, and we want somehow to combine them together. Remember, the entire process of backpropagation is that we are going from the end of the graph one operation at a time, and we want to combine this information together to pass it along to other operations that are above us in the graph. Right? And the correct way to combine that information turns out to multiply them together. By multiplying them together, we get that other quantity, which is called downstream slope. And these values, these slopes, will be passed along to the other nodes in the graph above us. So this local primitive in the graph doesn't need to be aware about all the other computations around it. It only needs to be able to kind of compute the influence of change in its input on its output. And this local slope, in other words, which we exactly just computed. And then that other quantity representing the influence of the change in the output of the current operation on the output of the entire graph, in other words, this upstream slope, will be passed along to the current operation. And these two quantities can be, this local and the upstream, they can be combined together by simply multiplying them. And this will represent this downstream slope. So we just took the local influence of the input to an operation on the output of the same operation, and we combined that together with the influence of the output of that operation onto the output of the entire graph. Let me go ahead and add this to a larger computational graph. Here in blue, we have the local slope for the current operation, the absolute value. So this is a slope of 1, which we computed previously inside that blue box corresponding to that operation. We already discussed that earlier. So I took that slope of 1 from there. Semantically, this local slope represents the influence of the input to that operation on the output of the same operation. And in addition to that, we have that other quantity, this upstream slope here, which semantically represents the influence of the output of that operation on the output of the entire graph. And just as discussed before, we want to combine two of these quantities together, and the correct way is to chain these two, or multiply them together. Let me move that arrow closer as to visually, hopefully represent the chaining of these slopes, or combination of these slopes. And the computation that we need to perform here is, just as before, local multiplied by the upstream. In this case, the computation will be 1 multiplied by 1. The answer is 1. So our downstream slope here is 1. Let me go ahead and mark this computation as complete. Right here. You may notice that here I assigned different semantics to the colors. So the red color represents that the computation is complete. But we're actually still not done, because of course there is more operations in our graph to go. Specifically, the next node in our graph that our backpropagation algorithm will see, going from the end of the graph, is the subtraction operation right here. And just as before, we'd want to compute the local slope for that operation. In other words, we want to compute influence of each one of its input to that operation on the output of that operation. And to do that, we'll use the two possible approaches. One of them is by using this visualization method, where we actually plot things, and not only will be able to compute the actual slopes for that operation, but also we'll be able to gain some visual understanding of how these slopes actually came to be. But in addition to that, we'll actually use the second and separate approach for computing these slopes, and this is by using the rules of calculus. And don't worry, it'll actually be very, very simple. So let's start with the first approach. And here, just as before, we're about to go inside that green box right here. And you may remember the semantics of that. Every time when we are going inside the box, that means that for a moment we forget about all the other computations inside our graph, and we only focused on that single node that we are currently looking at, which in this case is a subtraction operation. You may also notice that the color of this box is actually, it matches the color of the subtraction node in the graph. They're both green, and this is hopefully to make it even further separation and make it visually clear that we're only talking about the subtraction node for now, and the calculations are happening inside that node. So for a moment, we forget about all the other computations in the graph. Now, you may notice something interesting. That node is actually different from what we previously saw, in that this node has two inputs. The previous absolute value node had only one input, but the subtraction node actually has two. And when computing these slopes, in other words, when computing the influence of the inputs on the output of that operation, we actually would want to disentangle the contribution of each one of these inputs. In other words, we want to know exactly how much each of the inputs contributes to the final output in that operation. So let's go ahead and zoom into that box and focus on these computations. Let's firstly discuss the slope. Let's first compute the slope for the first input. As you may notice here, so we're interested in computing how much changing the first input of that operation influences the output of that operation. And to do that, we can pick some value for the second input, for example, these two right here, and we can just fix it in place, right? So we can just, we will not modify that value. Instead, what we will do is we'll try out different values for the first input, and we will see and note how much does the output of the circuit change when changing this first input. So let's break it down and go step by step. We'll use this loose definition of the derivative as before. Now, according to the definition of the derivative, we need to take some input to our function being the subtraction operation for now. So let's pick the first input, let's say +2, and we feed it in we replace it into our formula here. In other words, we execute our operation on these inputs. And the resulting value, let's say, is 0. This is the output of our operation. Then, according to the definition of the derivative, we need to now modify our input by some margin. So here, let's say the previous input was 2, now the new input is 5. So this is our modified input. And then again, we feed it in to our operation. But now we're feeding this new input, which results in this value of 3, let's say. So this is the new output of our function. Now, according to the definition of the derivative, we need to subtract the two of the outputs. So remember, the first output that we got from our operation is 0, and the second output that we got from our operation is 3. So we need to subtract these two. We already discussed this, so please feel free to pause the video and revise the definition of the derivative. And subtracting the two visually corresponds to this red arrow that you see on your screen. So this is the change in the vertical direction, in the output. And then we need to, according to the definition, we need to divide this change in the vertical direction by the change in the horizontal direction. So what actually is computing, the definition of the derivative is computing the slope. Another way to see that is the two of these points that you see on your plot, they actually form a line, and what we want to compute is the slope of that line, right? So let's go ahead and actually substitute these actual values. So the change in the vertical direction is, we went from 0 to 3, so the change is 3. The change in the horizontal direction is, we went from 2 to 5, so the change in the horizontal direction is also 3. And when we divide these two together, we get a slope of 1. Let me clean up the plot. That's exactly what we got. We got a constant slope with a value of 1. Now, keep in mind what this slope of 1 actually telling us. What it tells us is that when we slightly modify the first input to that subtraction operation by some margin, right here, the output of that operation will increase by the same amount, right? It will increase because the slope is positive. So this is the semantics of the slopes that we just computed. Now, in practice, this visualization method is not actually used because it is not precise. So instead, people use this derivation method. So people use rules of calculus to actually, accurately derive the slope. So let's go ahead and use this approach separately to compute the same slope. So here's the definition of the derivative that we discussed earlier, right here. And this is our current function that we're looking at, the subtraction operation. So to do this derivation and compute the slope with respect to the first operator, what we need to do is to take that function of subtraction operation and substitute it in to the definition of the derivative. When we do that, we get this expression right here. Now, if you're not in the mood of actually doing the derivation yourself, you can simply use Google and here actually paste it in the same exact equation that I just showed you. And the solution to our equation is 1, right? And if you're interested, you actually go step by step and see the reasoning, how do you arrive to that conclusion. Let me go back for a moment. And this turns out exactly what we computed previously. So by our visualization method, the slope that we computed was 1, as you might remember, right here. And it turns out that it matches exactly this a precise numeric derivation that you can get with calculus for this specific case. But in general, the derivation is much more precise. So you see that the answer that we got from the derivation matches what we got with our visualization method. Now, what we just computed so far is the influence of the first input to that subtraction operation on the output of the subtraction operation. But this is not it, because the subtraction node actually has two inputs, not one. So what we need to do is separately compute the influence of the second input on the output of this operation, right here. And we can do this by selecting some value for the first input to this operation, let's say 3, and fixing that in place. So we will not modify that value. Instead, we will fix that value unchanged, and we will try out different values for the second input, and we will see and record how much does the output of this operation will change. And this actually will tell us the influence of the second input on the output of this node. It will tell us this local slope. So let's go ahead and do this. We'll use our loose definition of the derivative again. We need to pick some input, and let's substitute it in place of this second input to the subtraction operation, and we'll get the output value of 3 in this case, right here. Now, according to this definition of derivative, we need to modify that value for the second input to our operation in this case. And let's say the new value of our input is 3. Just as before, we substituted this 3 in place of this second input to our operation, and we get our answer, our output of this operation, which is 0 in this case. Now, the definition of the derivative tells us to subtract the two of these outputs from our operation. Remember, the first output that we got was 3, and the other output was 0. So when we subtract the two, we get the change in the vertical direction, which is -3. So when we divide this change in the vertical direction by the change in the horizontal direction, we get the answer for our slope, which is -1. Let me clean up the plot here. That's what we just computed. The slope is constant with a value of -1. So you see that our line actually goes down, right? Because it decreases because the slope is negative. And keep in mind what the slope is of -1 actually means. And what's semantically telling us? What it tells us is when we slightly increase the value for the second input to the subtraction operation, the output of this entire node will decrease by the same amount. It will decrease because the slope is negative in this case. Now, to verify our visual understanding here, we can use the rules of calculus again as a second approach to compute this slope for this input. And in general, the visualization approach is not used, rather this derivation method is used because it's more precise. So here, highlighted in red, you see the definition of the derivative. And right below that, this is our current function, which is the subtraction operation. Now, to compute the slope of the output of the subtraction operation with respect to the second input, we want to substitute this f right here, our current formula of our current function. We want to substitute it in place of this f inside that formula. And when we do that, we get this equation right here. Now, just as a side note, notice that the definition of the derivative only has one input, and it evaluates the function twice on the original input and on the perturbed input. But unlike the definition of this derivative, our current function has two inputs. And because we're interested in changing the second input and seeing how does the output of the circuit change, here when we substitute our function into that formula, notice that we are perturbing or changing the second input to that function, and we are changing it by this margin h. If you are not in the mood of deriving this yourself, we can actually use Google just as before and paste in that equation and get our answer here. So these two cancel out and the answer is -1. If you're interested, you can explore step-by-step reasoning how you arrive to this conclusion. Now let me go back. You can verify the derivation by doing it yourself if you're interested. The answer is -1. Now again, this turns out to match exactly the slope that we've computed by sort of visually plotting things. But again, in practice, this visualization method is not used. Rather, this precise method of deriving using the rules of calculus is used to compute the slope of each input. Okay, great. So at this point, we computed the slopes of the output of the subtraction operation with respect to both of its input, right? So the slope of this output with respect to the first input of the subtraction operation is +1 right here, and the slope of the output with respect to the second operation is -1 right here. Let's go ahead and plug these results, slopes for both of these inputs to the subtraction operation, back into our larger graph, right? So let's go back to our larger graph. As you remember, these local slopes and the upstream slopes, these are, at the moment, two different quantities. The local slope semantically mean how much does each one of the inputs to this specific operation that we're currently looking at, this subtraction node, how much does each one of its input influences the output of this operation of the subtraction node. On the other hand, the upstream slopes, highlighted in red, indicate how much does changing the output of this circuit of the subtraction operation changes the output of this entire graph. These are two different quantities that we want to combine together. We want to chain the influence of the current node into this larger computational graph. And as we discussed previously, the correct way is to multiply them together. So what we need to do is we need to multiply this upstream slope with each one of our local slopes. We'll need to multiply this one at a time. Let's consider, first of all, this first local slope for the subtraction operation. And here I'm moving it down in our plot to sort of visually represent that we are chaining or combining these two values together. And the correct way, as I discussed, is to multiply them. So we're multiplying these two values, and the result is 1, of course. So let me go ahead and mark that part of the computation as complete. I'll highlight it in red. So here, you may notice that I assigned different meaning to the colors. So the red color means that we have completed the computation in that part of the graph, while the blue color means that the computation is still not done, and we still need to perform some calculations there. And exactly, we see that there is the slope of the output of the subtraction operation with respect to its second input is still highlighted in blue. So we need to we still need to chain that value together with the rest of the graph. Let me visually bring that closer. And the correct way again is to multiply these two values together. So this upstream slope with this second local slope. So we need to multiply -1 by 1, and the result is -1. So this value stays unchanged in this case. And let me go ahead and mark this part of the computation in red, meaning that we have completed chaining each of the inputs of the subtraction operation with the rest of the graph. We're still not done with the rest of the graph. There are a few more nodes to go, and specifically the next node that our backpropagation algorithm will see is this addition operation. So let's go ahead and compute the local slopes for this addition operation. So just as before, we are now focusing only on this addition operation, and we forget about the rest of the computations in the graph for now. So here we are going inside of this yellow box, which matches the color of this addition node in our graph. So that is hopefully to visually illustrate that we are now talking only about this addition operation, and we forget for a moment that this computation is embedded in this larger computational graph. And again, we'll use the two of our favorite techniques for computing these local slopes. One of them is to plot these values and visualize the result and compute the slope in this way. And the other separate approach is by using the rules of calculus. So which is more precise. So we will do both of them. So this addition operation has two inputs, and just as before, we want to disentangle the influence of each one of these inputs on the output of this addition operation. So to do that, we need to fix each one of our inputs to this operation one at a time, and then change or modify the other input. And each time we want to see how much does the output of this circuit change. And this will effectively tell us the slopes that we want. So let's go ahead and do this. Firstly, let's compute the slope of the output of this operation with respect to the second input. So to do that, we need to pick some value for the first input and fix it in place. Right? So here, the first argument to this addition operation is fixed. We are keeping it constant. And we want to try out different values for the second input to this operation to see how much does changing that second input influences the output of this operation. So let's go ahead and do this. We'll use our loose definition of the derivative one more time. So we need to pick some value for the input. And this is our second input to this operation, and we substitute it in place for that input, and we execute or call this operation on this pair of inputs. And the resulting value right here is 0.5. Visualized here as well. Then, according to the definition of derivative, we need to change our input by some margin. So our previous input was 0, our new input is 5. And we, again, plug it in place of this second input to this operation. And we run our operation on this new pair of inputs. The resulting value is 5.5 in this case. Now, following the definition of the derivative, we need to subtract the two of the outputs. Our first output was 0.5, and the second was 5.5. So So the change in the vertical direction visually here can be represented by this line. And I will not show all the computations here, but if we divide the change in the vertical direction by the change in the horizontal direction according to the definition of derivative, here we'll get a slope with value of 1, so the slope of 1. And another way to see this, these 2 points here, they form a line. Let me try again. And this change in the vertical direction divided by the change in the horizontal direction is simply the slope of that line. Okay, let's go ahead and clean our plot a little bit. That's what we just computed. Our slope is constant with a value of 1. Now keep in mind what the slope of 1 means semantically. It means that if we change the second input to this operation by some amount right here, the output of this operation will react by increasing by the same amount, right? It will increase because the slope is positive. And just as before, let's verify our results that we got here, the slope of 1 that we computed by visualizing, essentially by visualizing things. Let's verify that with a more precise method, which is using the rules of calculus to actually derive these results. To do that, we will need our definition of derivative again, and the current definition of the current function, which is the addition operation. Now, to compute the slope of the output of this operation with respect to the second input, we need to substitute our formula for addition in place of this f inside the formula for the derivative. And when we do that, this is the equation that we get. Now, if you don't want to derive it yourself, you can paste it into Google, and the resulting value is 1. Just as before, if you're interested, you can explore a step-by-step explanation of how do you arrive to this answer here. Now, so the answer is 1, and this is matches whatever we computed using our visual approach, right? So previously we got the slope of 1 here, and this exactly matched what we computed by actual derivation. So that's great. Actually, this addition has not only one input, but the second input as well. Here I omit computing the slope of the output with respect to the first input, because it turns out that for addition, the slope of the output with respect to both of its input is actually 1. So I'll just skip that for now. If you're interested, you can compute it yourself. So let us go to our larger graph and incorporate these slopes for the addition operation into that larger graph. So what we just computed is 2 of these values right here. The slope of the output for the addition operation with respect to its first input is 1, and the slope of the output of the addition operation with respect to its second input is also 1. And remember, these local slopes semantically represent how much does each one of the inputs to the current operation, which is addition, influence the output of this operation. On the other hand, we also have this other quantity inside our graph, which is this upstream slope, which semantically represents how much does changing the output of the current operation of the addition node changes the output of the entire graph. So these represent 2 different semantic quantities which we want to combine together. And the correct way to do that is, of course, using the chain rule, as we discussed previously. So we need to multiply them together. So let's go ahead and multiply this upstream slope with each one of our local slopes. So let's start with the first local slope for the addition operation here, and I'm moving it closer to the upstream to visually represent that we are chaining or combining them together. And the calculation that we need to perform here is multiply this value by this value, which results in -1. So this value actually changes. Let me replace it by -1. And let me go ahead and mark that part of the computation as complete. Because remember, just as before, the red color here has the semantics of that we've done computing that part of the graph here. On the other hand, we still have the slope of the output of this addition operation with respect to the second input, which we haven't completed quite yet. So let's go ahead and do that. Let's combine that second slope for the addition with the upstream slope. And again, what we need to do is multiply this -1, this upstream slope, with this local slope of 1. And the resulting value is, of course, -1, so the slope will change. And its new value is -1. Let me go ahead and now mark this part of the computation as complete. All right, great. So what we just did is we combined together these quantities and we chained the influence of this current node that we just looked at, this addition operation, into this larger graph. Now there is one final operation in our graph that our backpropagation algorithm needs to visit, and that is this multiplication node right here. So let's go ahead and compute the local slopes of this operation. Here, as before, we're going inside this box, which semantically represents that we're only focusing on that single operation for now and forget that this operation is embedded into this larger computational graph. You may also notice that the color of this box actually matches the color of the node, this multiplication node in the graph. They are both pink. That's hopefully to make it clear visually that we are only focusing on that single operation for now, and everything inside that box corresponds to the computations for that single multiplication operation. Now, let's use the two of our methods, the visualization method and the derivation method, to compute the local slopes for the inputs of this multiplication node. Now, this multiplication operation actually has two inputs. So, just as before, in these cases, we need to disentangle the contribution of each of the inputs to the output of the node. So what we will do in this case, we will fix one of the inputs to this function in place, and we will try different values for the other input to this operation, and we will see how much does the output of this node change as the result of us changing one of the inputs to this operation. And this will effectively give us the slopes that we want. So let's go ahead and firstly compute the slope of the output with respect to the first of the inputs to this operation. So with respect to this A input right here. So to do that, we will fix in place the other input, and we will try different values for the first input, and we will evaluate that function a couple times. You will see how much does the output of this function change as a result of us changing the input to this function. So I will not go over all of this step by step here. This is very similar to what we discussed previously. We are using our loose definition of the derivative here, and essentially the change in the vertical direction here is 4, and the change in the horizontal direction is 2. When we divide these two numbers together, we get the resulting slope of 2. So another way to see this, the two of these points, they form a line, and the slope of this line is 2. Let me clean up the plot here. This is exactly what we computed. Now, this is interesting. What this 2 actually means, where does it come from? Well, actually it turns out that this 2 corresponds to that other input, to the second input of this operation that we kept fixed. Right? So that's a curious observation. So in other words, what it means is, if we change one of the inputs to this operation, the output of the circuit will react proportional to the other input to this operation. And we'll return to this in a moment, but keep in mind what the slope of 2 means, right? It means that if we slightly change the first input to this operation by some amount, the output of the circuit will react by increasing, in this case, because the slope is positive, by twice that amount, right? So this is what the slope of 2 means. And just as before, we can verify our numbers here that we got by visualizing, by plotting things. We can verify these slopes by using the rules of calculus. So just as before, here we have the definition of the derivative, and here we have our current formula for the operation that we are performing, this multiplication operation. And what we want is to substitute this formula for our current operation, multiplication, inside that formula for the definition of the derivative. And as a result, we get this equation right here. Now, if you don't want to derive this yourself, you can paste it into Google. And you see that the solution to this problem is B. Let me go back. The solution to that problem is B, which is exactly the same as we computed right here. And remember that we don't need to plot or visualize them in practice. We can simply derive them using calculus. We're still not done with this multiplication operation because that's a binary operation, it has 2 inputs. So far, we only computed the slope of the output of this operation with respect to its first input. Now there's also the second input to this function, which we also need to consider. So let's go ahead and do this. Here, we are interested in computing the slope of the output of this operation, now with respect to the second input. And to achieve this, we now fix the first input in place, and we try out, so we fix the first one in place, and we try out different values for the second input. Again, we are using our loose definition of the derivative here. I will not go step by step. Feel free to pause the video and do it yourself if you are interested. But in short, the change in the vertical direction is 2, and the change in the horizontal direction is 4. So the slope of the output with respect to the second input here, if we divide these two numbers, is 0.5. And let me clean up the plot here. Again, we see this interesting observation here that what this 0.5 actually means, where does it come from? Well, this is actually our first input that we fixed here, right? So it indeed turns out that for the inputs to this multiplication operation, if we change one of them by some amount, the output of the circuit will react with a magnitude corresponding to the other input, right? So in this case, we changed the value of b by some amount, and the output of this operation reacted by changing with the magnitude of the other input, of the a input to this operation. And keep in mind what the slope of 0.5 actually means. It means that if we slightly increase the second input to this multiplication operation by some amount, the output of the circuit will increase, because the value is positive, it will increase by half of that amount. This is what the slope of 0.5 means. And just as before, we can verify our calculations here using the more precise method. Using calculus, we can derive the answer. This is our definition of derivative here. This is the definition of the current function that we're looking at, the multiplication operation. And just as before, we substitute it in place of this f in the formula. Now we're getting this formula right here, this equation. And if you don't want to derive it by hand, you can paste it into Google. Here I've done this, and the answer is A in this case. And again, it matches exactly what we computed for this input using our visualization method. Okay, great. So we have just finished computing the slopes output of this multiplication operation with respect to each one of its inputs. Now let's go ahead and write it into our larger computational graph. So what we just computed inside that pink box corresponding to the multiplication operation is the local slopes for each one of the inputs of this operation. And what we learned is that if we change one of the inputs to the multiplication operation by some amount, the output of the circuit will react by changing with the magnitude corresponding to the other input, right? So in other words, the slope of the output of this multiplication operation with respect to the first input is the second input. And the local slope of the output of this operation with respect to the second input is its first input. That's what we just computed. But separately from that, we have this other quantity inside our graph, which is the upstream slope. Now keep in mind the distinction between the two. The local slopes, in other words, these arrows in blue, semantically what they're telling us is how much will the output of the current operation, multiplication operation, will change if we slightly change the values, the inputs to this operation. On the other hand, this upstream slope, this value highlighted in yellow here, it has different semantics. And what this is telling us is if we change the output of this current operation, how much will the output of the entire graph will change? So we see that this upstream and local slopes, they have different semantics, and the correct way to combine them together is to multiply them. So this is the chain rule in calculus. So let's go ahead and just as before, just with all the previous operations in our graph, let's go and combine one local slope at a time with this upstream slope. Now we want to combine or chain that value together with the upstream slope. So here I'm moving it physically closer inside our diagram to this upstream value. So to hopefully semantically, visually represent that we are combining these values together, right? The correct way to do this is to multiply them. So we need to multiply this -1 by, in this case, parameter 1. So the resulting value will be negative parameter 1. So the sign here will change. Let me go ahead and mark this part of the computation in red. And remember, we have the semantics here that color red represents that we have finished this part of the computation, while the color blue represents that we have still some of the computations to do there, right? And indeed, we have this final arrow highlighted in blue right here, which is the slope of the output of this multiplication operation with respect to the second input of this multiplication operation. So let me go ahead and, again, move it closer in our plot to the upstream slopes. I'm connecting them in our diagram to reflect that we are combining or chaining these two values together. Just as before, we need to multiply this upstream slope, which is this value, this -1, by this local slope, in this case, input. So the sign here will change. The result of it is negative input. And let me go ahead and mark this part of the computation in red, denoting that we have finished this part of the computation as well. Now notice that our backpropagation algorithm that we just simulated by hand one step at a time started from the end of the graph, and it considered one operation at a time, right? Sort of in this upwards manner, we went from the end of the graph to the beginning. Now at this point, we have successfully reached both of the values that we were interested in, namely these two of the model parameters. Right? Remember that our original goal was to compute how much does changing each of these parameters influences the final output of the graph. And the final output of the graph being the loss value, right? The loss value quantifies how bad or good a given model prediction is. If the loss value is small or low numerically, that means that the model predictions are good. So therefore, we were interested in finding out how does changing the parameters affect this final output of the graph, this loss value, right? And the reason why we were interested so that we now, if we know how does it affect the final output of the graph, we now can change these parameters in such a way that would minimize that loss value, which would correspond to maximizing the quality of the model predictions. Now notice, by this time, we have reached both of our parameters starting from the end of the graph. That means that now our backpropagation algorithm can terminate. Our parameters are the only values inside of this current computational graph that we can freely adjust, so that we will take that freedom of adjusting them to drive the output of this computational graph down. The output of this computational graph is the loss value. Please feel free to pause the video and revisit the part where we discuss about defining the loss functions and the semantics of them. But in short, we took the effort of designing our loss function to encode our human knowledge for this particular task of what does a better or worse model prediction mean, right? And when the loss value is high, that means that the model prediction is far from the ground truth label, that is, the model prediction is incorrect. Therefore, we want to drive the loss value down, which will in turn correspond to increasing the quality of the model predictions. And the only two levers in this particular computational graph that we can freely adjust are these two model parameters. We cannot adjust these other values highlighted in yellow because this is not meaningful. For example, even if we know how much does changing, let's say, this value, how much does changing the input will affect the output of this entire graph, this is not valid to modify the input in arbitrary ways. Similarly, it is not valid to modify the label in arbitrary ways, even though it will help us if we change these values, right? Because we know exactly by now how to adjust them to bring the output of this computational graph down. And why do we know this? Well, because we know the slopes associated with each one of these, right? But this is still not valid to modify them, because the inputs and the labels are wherever they are. This is defined by the dataset, right? And the datasets are collected from the real world. These are some observations grounded typically in the real world. It is not valid for us to change these observations, because it would mean that we are undermining the semantics of the dataset itself, right? Because this will no longer be the same dataset once we adjust these values. So this is not valid. Instead, what is instead valid is to modify our model parameters, these values highlighted in pink. You can think of these parameters as being some internal variables of the model, and therefore we are free to modify them to drive the output of this graph down. The more we adjust these model parameters to bring the prediction from the model closer to the actual label, the more we say the model learned a particular task. So here I grayed out the irrelevant parts and left only the parts of the computation that led to our learnable parameters. How would the output of this entire computational graph would change if we slightly increased each of our model parameters? Well, let's start with our first parameter to begin with. We see that the slope of the output with respect to this model parameter is negative input. When we executed our model, that numeric value was -2. Now, let me go ahead and substitute that -2 right here, and we get this negative sign first, don't forget, negative, and -2 itself. The result is +2. So the slope of the output with respect to our first parameter is +2. This means if we slightly increase the value of our first model parameter, this value right here, the output of our entire computational graph will increase by twice that amount, right? So it will increase because this value, 2 right here, is positive, right? So the slope is 2. Therefore, if we perturb the value, the output of the graph will react by twice that amount, right? Now, similarly, let us consider how the output of this entire computational graph will change if we slightly increased now our second model parameter. So we see that the slope of the output of this computational graph with respect to the second model parameter is -1, which means if we slightly increase the value of this model parameter, the output of the entire computational graph will decrease by the same amount. Now, it will decrease because here the sign is negative, and it will decrease by the same amount because here the value is 1, right? So there is no multiplicative interaction going on, right? Rather, whatever change we apply to our model parameter number 2, the output of the graph will decrease by the same amount. In addition to that, there is a separate interpretation of the slopes that we computed. And that is, we can visualize all of our parameters of the model, which in this case we have 2, right? So we have 2 dimensions for our model parameters, represented by these axes. So one axis for our first parameter, second axis for our second model parameter, and we visualize it in the 3D space. So the third axis here is the value, loss value. Now, what does it remind you? Well, this is the loss landscape, right? So this is the relation, in other words, of all possible combinations of model parameters with respect to the loss values that a given combination of parameters can achieve, right? And let's go back and revisit our graph here for a moment. The value of our first model parameter is -1, the value of our second model parameter is +1, and the loss value is +2. These are exactly the same coordinates as demonstrated on this plot. Specifically, the value of the first model parameter is -1, the value of the second model parameter is +1, and the loss value, which is somewhere on this axis, on the vertical axis, let's say it's right here, +2. Therefore, I plot a point corresponding to the 3 of these coordinates. Now, in addition to the values of the parameters themselves, what we computed, and what's the more important thing for optimizing the model, are these slopes of the output of our model, of this computational graph, with respect to each of the model parameters, so here highlighted in yellow, right? And in this plot, we can visualize these slopes, because we have 2 slopes, one corresponding to each of our model parameters. We can visualize that in a 2D plane, right? Same dimensionality as the number of our parameters. So indeed, this yellow plane that is slicing through this loss landscape by this arrow here, this yellow arrow, I try to illustrate the direction of the greatest increase of that plane, right? So each one of our slopes with respect to the model parameters that we computed, they show a direction of the greatest increase of the function. Of course, we're interested in decreasing our loss and not increasing that. So therefore, we can adjust our model parameters in the opposite way of the greatest increase, right? So if the plane increases in that direction, highlighted by the yellow arrow, we can step in the opposite direction. And that would tell us the greatest decrease of the function. In other words, it will tell us exactly how to adjust our model parameters to now minimize the loss. So we can take that direction as guided by our direction of the greatest decrease of this 2D yellow plane. We can try out this value as a new setting of the 2 of our model parameters. And when executed on the same input, the setting of these model parameters, these new model parameters, should produce a lower loss value. Again, because we purposefully stepped into the direction of the greatest decrease of that yellow plane here. And that yellow plane simply corresponds to the 2 of our slopes that we computed, but now visualized in a single plot, right? This is the second visualization that we saw. But alternatively, and equally valid way of visualizing this, is to visualize them as 2 different plots, right? Don't be confused about the following. You may remember that we used the term local slopes many times here, and you're used to seeing these local slopes associated with each of these operations. Now, these values are not local slopes, and that's because we did use local slopes, but then we wired them into this larger computational graph by multiplying them with the upstream slope. So these values that we got as a result of our entire backpropagation process, these are not local slopes. These are slopes of the output with respect to these model parameters.